Today we're going to take an exit off of the exponent rules highway after having done zero and negative exponents. And we're going to learn or remember, depending on which camp you're in, scientific notation. And the reason we're inserting it here is because in our next three exponent rules, we will be using those exponent rules on scientific notation. So we're just going to take kind of just a little break to remind ourselves and or learn what scientific notation is. We're going to write numbers in scientific notation. We're going to take numbers that are in scientific notation and write them in standard notation. And we're also going to compare numbers that are written in scientific notation. So we have to start with the question, what is scientific notation? And what is it useful for? So I'm going to start talking about the mass of the Earth. And we need to remember that the mass is how much matter there is in an object, how much stuff. It's not the weight, it's how much stuff, how much matter is in the Earth. And so I went out and I Googled it, and here is the mass of the Earth. Holy cow. Let's see, 5 septillion, 974 hextillion, 200,000 quintillion kilograms. Now, just to let you know, a kilogram is kind of like, I don't know, a small bag of onions if you go to the grocery store, okay? And obviously, our concern is a big, wide, help. Can you imagine trying to read that number, work with that number? It's just an absurdly large number. So what we need is a way to write really big numbers and, oh, by the way, really small numbers more easily. And that's what is scientific notation. So I'm going to start by taking a number, and when we have the number 560,000, that is written in what is called standard notation. That's what we're used to writing. And I'm going to convert it to scientific notation. By definition, scientific notation has three parts. It has a number in front that has to be greater than or equal to 1 and strictly less than 10. So it has one digit in front, or I should say one non-zero digit in front of the decimal. So you wouldn't have 11.6, excuse me, you wouldn't have 0.007. You're going to have a number basically in between 1 and just less than 10. Now, here is where our scientists are going to mess with the mathematician. They are going to have the multiplication sign as an X, not as a dot. They didn't ask me. And then there's going to be a power of 10. So basically the way we do this is you look at the numbers at the front that are non-zero, the 5, 6, and you're going to write that as the start of your scientific notation, but you're going to insert the decimal so there is one place in front of the decimal. And that's why it became 5.6. Now I want you to go back up to this number and imagine that that decimal is sitting in between the 5 and the 6. And you need to multiply it by a power of 10. So basically look at the number of places that are on this side, right? So to the right, and you can see 1, 2, 3, 4, 5. So I have to kind of move that decimal 5 places to get it to the 5.6. So I'm multiplying by 10 to the 5th. Here's what I tell kids, because some folks can be really left-right challenged, is don't think about left-right. Look at this number, 560,000. That's a big number. I want $560,000. That is a positive thing, $560,000. So your exponent should be positive. So when your number is really large, a really big number will have a positive exponent on your power of 10. So 5.6 times 10 to the 5th is the same value as 560,000. It's just written in scientific notation. Okay, your turn. Can you please write 213 million in scientific notation? Okay, let's see how you did. You should have 2.13 would be the number in front. Times is your X and a power of 10. I definitely want $213 million. That's a positive thing. So my exponent is going to be positive. Now, how many places? That decimal is sitting at the end right now. How do I get it over there? Around the zero, around the zero, around the zero is 3. Keep going. 4, 5, 6, 7, 8. There are 8 places, 8 powers of 10, so this should be times 8. The number one mistake would only be to count the zeros. So if you take 2.13 and multiply it by 10 to the 8th, it is 213 million. All right, let's go in a different direction here. What if you have the scientific notation and you want to convert it back to standard notation? So you're going to have to move that decimal the same number of places as the exponent. And because it is a positive exponent, we're going to need to move it to make the number bigger. Okay, so basically what I do is I kind of covered it over, but I write that 36 and I put my cursor in between. And then I say, okay, I've got to move that decimal. My cursor is the decimal 6 places to make this number bigger because the 6 is positive. So I'm going to go around the 6, which was using up one of the places, and then add 5 zeros. And you can see the answers right here. So 3,600,000 is 3.6 times 10 to the 6. Can you change 2.74 times 10 to the 8 to standard notation? So the first thing I would have done was to write the 274. I would have put my cursor where the decimal is, saw the 8, and knew that I had to move it 8 times to make it bigger. Did you put 274 and 6 zeros? You do not add 8 zeros. You move the decimal 8 powers of 10. So you have to go around the 7 and around the 4, which used up 2, and then you need 6 more. So 274 million is the same thing as 2.74 times 10 to the 8th. What happens if we have really small numbers? So what if we are talking about like the size of an atom, or something really incredibly small? You could have a really small number. Now, if you look at this, money-wise, that's incredibly smaller than a penny. 0.01 would be a penny. Who cares about that? So this is a negative, right? Really small number is going to have a negative exponent. So again, we're looking for those non-zero numbers. So you see the 856. We're going to put the decimal. So there's one place, one number, one digit in front. So it would be 8.56. And now I need to say, how many places did I move this decimal to get it where I want it? Around the 0 is 1, again 2, 3, 4, 5, and around the 8 makes 6. And it has to be a negative exponent because this is a ridiculously small number. So some of the mistakes I will see here is people forgetting the negative and only counting the zeros and putting a -5 here. Okay, can you take this number and write it in scientific notation, please? And did you get 6.6 times 10 to the, now here comes the tougher part. Now, first of all, it should be negative. And then remember that I had to go around the 4 zeros and the 6. So the decimal moved 5 places. So basically in scientific notation, if you see a power of 10 that is negative, we're talking about a really small number. And if you see a power of 10 that is positive, we're talking about a really big number. Okay, so now let's go back the other way. Can you write this in standard notation? So again, take that number and kind of take the decimal out and just put your cursor where the decimal was. Look at your exponent and noticing that it's negative, move the decimal to make this smaller. So in this direction. So around the 2 would use up one of those -8, and then you should add 7 zeros. So it would be 0.70201 is the same value as 2.01 times 10 to the -8. Your turn. So again, write the 3.5 without the point. Put your cursor there and move the decimal 4 places to make it smaller. Did you get 0.00035? Count those zeros and make sure you didn't put 4. So one of the advantages of having numbers in scientific notation is it is amazingly easy to order them, like least to greatest or greatest to least. So Comparing numbers in scientific notation, this table shows the top US cities visited by overseas travelers. And we have all the numbers written in what we think are scientific notation. Now, again, check to make sure they are all written in proper scientific notation. Check to make sure there's only one number in front of the decimal and that there is one digit there other than 0. And, make sure it's a power of 10. Now, to order them, after you've made sure they're all in proper scientific notation, use your powers to determine, now, wait a minute, we want to go, in this case, from least to greatest. So find your smallest power of 10. And that would be Boston and Metro DC. Now, if the exponent is the same, use now the number in front and say who's smaller there. And notice Boston at 7.21 would be smaller than the 9.01. So Boston would be 1 and Metro DC would be 2. Now we're going to move on to the next highest. And believe me, everybody else is a 6. See that? So all of the 5 remaining cities are in contention for place 3. So now go out in front, and which of the numbers out in front is the smallest? And you'll notice Las Vegas will come in at 3rd. And then we will head down to the 1.6, then the 1.8, then Los Angeles, and New York City is by far the most traveled to city from overseas. And if you had just looked at the number in front, you might have thought it was Metro DC, but you've got to look at the power 10, which is called the magnitude of the number. Now, what if those numbers, normally, guys, we would kind of be writing these in order. I'm kind of taking a quick way of just putting the numbers out here. So first would be Boston, second would be Metro DC, and so forth. Okay, so let's take a look. What if they're not in proper scientific notation? What do I mean by that? So at first glance, some numbers look like they are. So for instance, look at this right here in the middle. It's got a number times a power of 10. But oftentimes, this number in front may not be in proper form. See, 34.5 is greater than 10, greater than 9.99 actually. So we need to fix this to be in proper scientific notation. So basically what we're going to do is we need that decimal to move so that it's in between the 3 and the 4, right there. When we moved that from 34.5 to 3.45, we kind of took out a power of 10. We made it smaller by a power of 10. We took away a power of 10. So what we need to do is go to the back of the number. Remember, this is a whole number here. We need to go to the power of 10 and compensate. So if we made the front number go down by a power of 10, we have to make the back number go up. These two are the same value, but this one is in proper scientific notation. Can you please try to do number 1 right now? Fix it. Okay, so the decimal here was after the 5, and it needs to be in between the 2 and the 6. So I'm going to make this number smaller by 2 powers of 10, and I need to compensate, do the opposite, and make that bigger. Did you get 2.65 times 10 to the 9? Okay, how about the next one? This time I had to make the number bigger by a power of 10. So I need to make this smaller. Whatever I do to the front, I kind of have to undo in the back. How's that? Okay, cautionary tale. The next 2 are where people will mess up. Take a careful look at your exponent. Try number 3 yourself. All right, so the 32 has to get smaller by a power of 10, smaller, so 3.2, which means this has to get bigger. -8 plus 1 is -7, not -9. Don't just look at it and say, oh, 9's bigger than 8. No, -7 is actually one number bigger. The negatives go in the opposite direction. If you got caught on that one, see if you can do 4 properly. This time, 1, 2, 3, bigger. So we need this to be 3 smaller. Did you put 8.8 times 10 to the -13, not -7? That's how we fix numbers who are not in proper scientific notation. This is going to become important when we go on to our next 3 rules and get back on the exponent rule highway. So I'd like to finish with one today that's going to kind of combine what we've done. What I want to do is put these four numbers in least to greatest. But what you need to do first is put them all in proper scientific notation. Once you have them in proper scientific notation, you're going to order them from least to greatest. When you finish ordering them least to greatest, so the first box will be them all in proper scientific notation. The second thing will be those scientific notation numbers written least to greatest. And then the red box is we're going to write them in their original forms. Okay, so start by putting them all in proper scientific notation. So the first and the second are bad, the third and the fourth are good. So did you put 3.21 times 10 to the 1, 2, 3, 4, and it's positive because it was a really big number? How'd you do there? This one needs to be fixed. I'm going to make it smaller by 2 powers of 10. I need to make that bigger by 2 powers of 10. And the last two are good. Okay, so now again, order least to greatest. Did you start with your negative? Then go, again, looking at the magnitude, the power of 10, it's really easy because nobody matches here. First, second, third, and fourth. Are you with me? And usually, to be honest, more on a standardized test than anything, they will kind of show the answer as the original. So this was an original, and this was an original, but these were written differently. So if this was a standardized test, an SAT, an SBAC or something, they would often write it like that, just so you know. So that is scientific notation. It really is something that most algebra students, once they do a few, they get the hang of it pretty quickly. We are going to get back on the highway of doing exponent rules, and what you're going to notice in the next few assignments is we're going to have scientific notation that we're going to use with our exponent rules. So now it's time to kind of get out there and practice everything we've done, and then when we get back to class, we'll get back on our exponent rules. I hope you guys have a great day. See you soon.